present a short review of the developments in this area on the past few years. And this is mainly because of the understanding, the better understanding of infinite dimensional algebras, its representation theory, and how we can implement this kind of mathematics to construct completely integrable equations, and also to construct its Soliton solutions and other properties. Many results on this subject were already known for some time, but the better understanding of this infinite dimensional algebras enable to understand this subject in a more uniform way, not to say in a more universal way. So I have divided this talk in 3 blocks. The first block, I'll discuss how to construct in a systematic manner a hierarchy of nonlinear equations of motion. They are all integrable. They all share the same conservation laws, which are interpreted as Hamiltonian of these evolution equations. So so far, this is the first block. The arguments are very general, but I'll use explicit construction for the simplest non-abelian Lie algebra, SL2. And the second block, I'll discuss the construction of Soliton solutions, and this will depend on representation theory of these infinite dimensional algebras. And the last topic, I'll discuss the construction of Backlund transformation, which we discovered that can be constructed in a universal manner for all the equations belonging to the same hierarchy. And this has a direct application on what is called integrable defects, which I'll explain at the end of the talk, and you may see in more details next week on Alexis' talk. So let me start with one transparency explaining the structure of the equations of motion in terms of this affine Lie algebra. You need 3 basic ingredients. The first ingredient is the choice of your Lie algebra. I use the hat to denote the affine version, and this affine Lie algebra is decomposed into graded subspaces. So you decompose your algebra into graded subspaces, and for this you depend on a grading operator. So the second ingredient is a grading operator that does this job. The third ingredient is a choice of a constant grade 1 operator, which I call E. So there are this E in turn decomposes your algebra in kernel and its complement. Kernel is everybody that commutes with E. So it's a concept, it's a very simple concept. So with these 3 ingredients, you are able to construct a family of equations of motion. They are all integrable and possess a common set of conserved charges. With these 3 concepts, you're able to construct what's called, mathematicians like to call a lax operator, which is the E that you have chosen, and A0. A0 is the most general linear combination of generators in M and in G0. So if you have a decomposition in graded subspaces, you know what G0 is. And if you have E, you remove the kernel and you know what M is. So you just take a most general linear combination, and then you have your A0 or your Lax operator. If you are a physicist, instead of Lax operator, you may feel more comfortable in defining a two-dimensional gauge potential, AX and AT. AX is essentially the Lax operator, and AT is a sum of terms which start in grade capital N and end in grade minus capital M. So you have a sum of graded terms unknown. And you plug your two-dimensional gauge potential into a zero curvature representation. The zero curvature representation is responsible for generating an infinite number of conserved charges. I don't want to go very much into this, but writing your equation of motion as a zero curvature condition, you have automatically an infinite number of conserved charges. Because of the graded structure which we have established at the beginning, you can decompose the zero curvature condition into a series of graded equations. So you see, the only term that has grade n plus 1 is this one. And then the next one, and then you decompose grade by grade, and you are able to solve for the dn's. You see, you start from the highest, you solve for dn, and then go to the next one, you solve for dn minus 1, until you reach d0, is the one before this one. And you see, this equation, which is the projection on the zero grade, is the only equation where dt acts in some operator. So this is the equation of motion, and it depends on d0 that is determined from the series of equations from top to bottom until you reach d0. And if you start from the bottom up, you have a non-local equation for d minus m, and the one before is another non-local equation for d minus m plus 1, and so on, until you reach d minus 1. So once you determine d minus 1 and d0 from the bottom up and from the top down, you determine your equation of motion. Obviously, d0 depends where you have started, depends on n. I just didn't put the indices not to make a very heavy notation. And obviously, d minus 1 depends on where you start, from the bottom. So this equation of motion depends on m and n. That's why I have added this index on the t. So for each n and each m, you have an equation of motion. So the collection of all these equations of motion constitute what we call integrable hierarchy. So you have a series of equations of motion, each of them evolving according to some t. There, okay? And the conserved charges are the Hamiltonians of the time evolution, of these time evolution equations. I'll give us an explicit example in a minute. So this is the example, which is the simplest non-abelian Lie algebra. It's just angular momentum algebra. H is just J3 and E plus or minus alpha J plus or minus. I take the grading operator. This choice of grading operator is called the principal grading. And the choice of my grade 1 operator, which is E. So my algebra, my infinite algebra, are those generators multiplied by some polynomial in some parameter lambda. And you see, it decomposes my infinite algebra into even and odd subspaces. As you can see, the HM, you see, lambda dd lambda is an operator that just counts the power of lambda. So you have a factor 2 is 2m, and h with h commutes, so it doesn't give you any contribution. The 2m plus 1, and you see you have lambda to the m, so you have 2m, and then you have 1 alpha, because h commuting with alpha is 2 alpha, and then you have a factor a half. So you have grade 2m plus 1. And also for the e minus alpha, you have an extra lambda, so you have twice m plus 1 is 2m plus 2 minus 1, which is the alpha with the opposite sign. So in this choice of gradation, the algebra decomposes in even and odd subspaces like what I am showing here. As you can see, the only term with 0 grade is H0. So it's just the ordinary H. So if you take m equals 0, just think about the positive hierarchy. You start with n plus 1, and then you go until you reach this equation of motion, which is the 0 grade component. And in particular, solving the highest grade equation, you determine dn to lie in the kernel. And the kernel has grade 2n plus 1, therefore capital N has grade 2n plus 1. And then you solve for dn minus 1 and so on until you reach d0, and then you plug into the equation of motion. As an example, I have evaluated for n equals 3, 5, and 7. So if you take A0, as I said, the only generator with grade 0 is H, and then you take a field in front of it, and if you do the calculation for n equals 3, you get this equation, which is known as the mkdV equation. If you do the same for n equals 5, it's a little bit more involving, a little bit more complicated, and you get this other equation. And you see you have one derivative with respect to the time, and then you have 5 derivatives with respect to x. And then you have more nonlinear terms and more complicated nonlinear terms. For n equals 7, the same. You have 7 derivatives with respect to x and more nonlinear terms. So all these equations, they come from a universal picture, which is the zero curvature and the same algebraic structure. Were you? Is a time, and I put an index just not to mix with the other t. It has to do with the highest grade. You see, it has to do with this capital N. So if I start capital N equals 3, I have 3, 2, 1, and then I have one equation, and then, yeah? Okay? So for each capital N, I have an equation of motion. So I have an infinite number of equations of motion. Each of them evolves according to some Hamiltonian, which are the conserved charges that I didn't say much. Okay? So what all these equations they have in common? They come from a zero curvature, and they have the same Lax operator. So you will see further on that the Soliton solutions, they can be written in a universal way. The Soliton solutions for all these equations. You just have to change a parameter multiplying the time component. And it will become clear why you need 5 derivatives or 3 derivatives. Okay. So let me just remark that V equals 0 equals a constant is a solution of all these equations. And this is obvious. Okay? And this solution I call a vacuum solution. I'm going to use later on. And a vacuum solution within the zero curvature notation means that this commutator is 0. You see, A0 is 0, and all the D's that I had constructed before are 0. The only one left is dn, which is the highest grade. And the highest grade has to commute with E. We knew this before because it had to belong to the kernel. And you see, a solution of zero curvature is a pure gauge. So if you have a zero, a mu satisfying a zero curvature, your a mu is a pure gauge for some t. So ax vac has to be some t0 minus 1 dx t0, and the same for the time component. So you can integrate. This is a derivative of a log. So you integrate, and then you find the group element that leads to the vacuum solution. So this will be important to construct non-trivial solutions. I'll start from the vacuum, and then I'll construct non-trivial solutions based on this vacuum solution later on. Before I get to the solutions, I want to discuss the negative hierarchy. Remember that I put all the negatives to 0, capital M to 0. Now I'm going to put capital N to 0 and consider the negative part of the hierarchy. So the negative part, you start from the bottom, and from the lowest you have a non-local equation. You have a derivative, and then you have the function there. Nevertheless, it's solvable. So you can solve. Obviously, you're going to have some non-locality coming up. And then if you go for the second lowest projection, you get d minus n plus 1, and so on, until you reach the zero grade component, which leads you again to the time component, to the time evolution of the same field A0. As an example, the simplest example is n minus 1. N minus 1, you have to solve these two equations. So the first equation is trivially solved if you parameterize d minus 1 as a conjugation of some grade minus 1 by some zero grade group element. And A0 will be written as a pure gauge within the same group element. So if you plug d minus 1 and A0 into this equation, you get 0 equals 0. It's automatically satisfied. And then if you plug these two these ansatz into this equation, you get this is the equation of motion. And this is known as a Lisnov-Saveliev's equation, or some people call the Toda equation. This is the Toda equation if t minus 1 is interpreted as t minus 1 and x are interpreted as light cone components. In the case of our example, I have SL2 example, in the principal gradation, what you get is the Sainz-Gordon equation. And if you interpret t minus 1 as z and x at z bar are the light cone components of the space-time. So the t minus 1 evolution is always a relativistic field theory. So mkdV, Sainz-Gordon, and all those equations that I have discussed are within the same hierarchy. They have the same algebraic structure. So let me go to the second simplest example. The simplest example was t minus 1. So this was a surprise that it came to us, because the second simplest example is t minus 2. And t minus 2, you have to solve these three equations. So you solve for d minus 2 here, and then you solve for d minus 1 in this equation, and then you plug on the last equation, which is the equation of motion. And this, you don't have a clever ansatz to solve in the closed form. You have to go by brute force, and then you write the most general a combination of d minus 2, d minus 1, plug in there, and then you eventually solve. And you see A0 was V times H, so I had to change variables. I change instead of V, I write my variable as phi, as derivative of phi. And if you want to invert, phi is the integral of V, which I denote as d minus 1, is the pseudo-differential operator. So d minus 1 of V is just the integral of V. And the equation of motion you get is this equation. And then you see you have two known localities, one in the exponent, so d minus 1 of V, which you can replace by phi, and then you have another d minus 1 of the exponential. So you have two known localities. For the Sainz-Gordon, I managed to change the variable and absorb 1d minus 1 in changing these variables. For t minus 2, I couldn't find a clever variable to make this equation local. But nevertheless, is a perfectly honest integrable equation. You have all these d minus 1s there. So the question now, what was a surprise, is the vacuum solution, because up to now, all those equations, they have v equals 0 was a solution. And now, if you have v equals 0, you see d minus 1 of 0 is a constant. And d minus 1 of 0 is a constant. So if I plug a constant inside this integral, this exponential comes out, and the integral is just x. And then this other comes out and cancels with this, and you don't get 0. So v equals 0 is not a solution of this class of equations. However, v equals v0, if you d minus 1 of a constant is v0x. And then you have integral of exponential of v0x and exponential of integral of exponential minus v0x, which has different opposite signs. So they cancel precisely. So this subclass of even negative integrable equations, the vacuum solution is a constant different from 0. Okay. So how long do I have? 20 more minutes. So the first subject I have already covered. Let me go now to the second subject, which is the systematic construction of Soliton solutions. So up to now, we know how to construct a series of equations of motion, all integrable, and with those properties I had already described. Now I want to construct the Soliton solutions of all those equations. So the idea is very simple. You know, we know the vacuum solution. We have already discussed the vacuum solution, either 0 or non-zero constant. So you know the vacuum, and the idea was whether exists a gauge transformation that maps the vacuum into some non-trivial solution. So the idea is very simple, but you have to prove that this gauge transformation exists. And it does. There are two solutions, one in terms of positive grade and one in terms of negative grade. So if your ansatz is theta plus as a product of positive grade generators, and then if you plug into this equation, you can solve grade by grade for the thetas. The same works equally well if you plug your theta minus as a product of negative grade, and then you plug it into this equation, and then you solve grade by grade. You can solve for the small thetas. So you can construct two gauge transformations that maps your vacuum solution into a non-trivial solution. But if you have two, uh, um, if you have two gauge transformations, you see your gauge potential, which is a pure gauge, is transformed as a multiplication of group elements, like this. But since you have two, the same group element is written in terms of theta plus times T0 or theta minus times T0. And they may differ by a constant, G. This constant will be very important. So you have your group element in terms of these two gauge transformations. So if you manipulate, multiply by theta minus 1, etc., you end up with this equation here. Theta minus 1 times theta plus is T0 minus 1 G T0. And T0 is what we have already determined before in terms of the vacuum solution. And we have to remind you that T0 contains explicit space-time dependence. So this is a very interesting equation, especially for physicists. A particle physicist, they like equations like this because you have positive grade to the right and negative grade to the left. Particle physicists, they always like to have creation operators to the right and annihilation operators to the left. And they call this normal ordering. So this side of the equation is normal order in terms of grade. Okay? And the right-hand side is not normal ordered because G contains positive and negative grades. So what we are doing is taking this expression, which is not normal ordered, and writing in terms of a normal ordered product. In mathematics, they call this kind of decomposition as a Riemann-Hilbert decomposition. So the Riemann-Hilbert decomposition is essentially is what physicists call normal ordering. Okay? So plugging theta plus and theta minus in these equations, you find, among other things, theta 0, which is the same B that we have came across before. So the idea here, since you have a normal ordered structure here, is to make a scalar product with the highest weight states, because theta positive grades annihilate highest weight states on the right, and theta minus annihilates all these highest weight states to the left. So the idea is to find an algebra which possess highest weight states. Therefore, I have to leave that simple realization of the affine algebra that I have started, just multiplying by polynomials on lambda my SL2 generators, and introduce a full extended Cox-Moody algebra. You have to central extend the algebra by adding these two terms. These two terms, physically, if you go and construct representation of these algebras, if you put all the H bars, you have an H bar there. So it's a quantum, is interpreted as a quantum anomaly. So it's a quantum mechanical term. So that representation in terms of lambda does not generate these central terms. But the central terms are necessary because otherwise the algebra doesn't have highest weight states. So if you extend the algebra, you have to add an extra field, nu, associated to the phi field, and also an extra term for the gauge potential. And then if you take the scalar product, you see that this equation, normal ordered equation, becomes this simple equation here. And this simple equation is very interesting because if you think a little bit. B contains the phi field, the field that appears in the equations of motion. On the other hand, this part here, T0, contains space-time explicitly. So you have an equality between field and a functional of space-time. And this is what we call a solution of the equation. Right? So the solutions of the equations are written in terms of a matrix element that I have to calculate. So now the problem is a technical problem. A problem is a technical problem to calculate this matrix element. Let's go back to the SL2 case. SL2 has two fundamental weights, lambda 0 and lambda 1. Lambda 0 is annihilated by everybody except the central term. That's why this exponential to the nu survives. And lambda 1 is annihilated by everybody except by central term and car by the h. So you have your phi in terms of the scalar product. So if you take the quotient gives you exponential of 5. Log of the quotient gives you 5. And if you differentiate with respect to x, the log of the quotient, you get your v field. So your solution for v is given in terms of a derivative of these two matrix elements that I call tau 0 and tau 1. And in fact, this was developed not in this way, but by the school of Kyoto, they had this kind of matrix element in terms of fermions acting on some from some Fock space. But is this kind of matrix element that you have to calculate. And remember that T0 had this, my T0 had this explicit space-time dependent, and the problem is that you have this G that you don't know, was a constant, was arbitrary until now. So the way you can calculate this matrix element is to choose this G as an exponential of some eigenstate of E plus or EM and E1. So the E's, they form this kernel, and you see the interpretation of the kernel is starting to pop up in the sense that they commute. And if you calculate the eigenstates of this of these elements, you can calculate the conjugation with T0. And the conjugation of T0, you pick up a phase. And this phase has explicit space-time with the coefficient, which is the eigenvalue. And this guy, F, is called the vertex operator. People from string theory, they know and they calculate this vertex operator in terms of oscillators. Oscillators called Fubini-Veneziano fields. So if your solutions are given in terms of the choice of this G. And the choice of this G is written in terms of these vertex operators. Let's go back to our solution. The one Soliton solution you can calculate, and okay, I forgot to say that these vertex operators, they have a property which I didn't write. They have a property of f square is 0. So if f square is 0, the exponential of rho times f has only one term, is linear in f. And if it's linear in f, you have your tau 1 and tau 2 is linear in rho, because I have already acted on the highest weight states. And your solution is given by derivative of this log, and rho is given by this exponential, and you have explicit space-time there. And now you can see that this formula solves all the equations I have given in the beginning. For n equals 3, n is 3. So if you take a differential, differentiate with respect to T3, you bring down gamma cube. But then you need to differentiate 3 times with respect to x to bring another gamma cube. So for gamma 5, n equals 5, you take 1 differential with respect to t, you bring down gamma 5, and then you need 5 differentiation with respect to x to compensate. But obviously, you have to differentiate the log, and then you have all the other terms to compensate that. So it makes a lot of sense, this formula, that solves all the equations that I have written before. Now, if you take G as a product of several F's, you get what we call multi-soliton solutions. And this is very simple. For those negative even, that V0 had to be different from 0, what you have to do is to find out a deformed vertex operator, and then the result is given by this exponential, and then you have a V0 plays the role of a deformation parameter. Okay? So how long? 10? Okay, I'll do it in, let's see. So this ends the second topic I wanted to talk about, and the third and more recent topic is what is called Backlund transformation. A Backlund transformation for the Sine-Gordon. Sine-Gordon is the second order equation. The Backlund transformation is a set of 2 first-order differential equations that involves 2 solutions, not any 2 solutions, but involves 2 particular solutions. And this is very interesting because it has a reasonably recent application. So for the Sine-Gordon, the Backlund transformation, which is this equation here, and another equation for t. So these equations are compatible because if you come and act with dt here, you need ddx here, you need ddx of phi 1 and phi 2 that you take it from here, and then you recover the Sine-Gordon equation. So phi 1 and phi 2 satisfy Sine-Gordon equation, and also they satisfy these equations, which is called Backlund transformation. So the idea, very recently, this was employed to describe defects, integrable defects. An integrable defect, you will see next week, is if you split your space, and then you suppose that you have one solution coming in, and then you have a defect in x equals 0, and then all of a sudden your solution becomes another solution. Obviously, energy and momentum are no longer conserved because you have broken homogeneity of space. So if you have one soliton solution, it hits the defect and becomes a 2-soliton solution. Neither momentum, energy, not even topological charges are conserved anymore. And this is because the defect absorbs and gives energy, momentum, and topological charge. And how do you describe this? You describe by an equation of motion for phi 1, a Sine-Gordon equation there, a Sine-Gordon equation for phi 2, and at x equals 0, you propose an equation like this, a Backlund transformation. So a Backlund transformation is something that transforms phi 1 into phi 2. And this was a very clever idea, and this was due to Ed Corrigan and collaborators. And the idea is, if you know Backlund transformation, you know how to describe defects. But you know Backlund transformation for Sine-Gordon. This, for 100 years, this is known. So what about the other models? I have an infinite number of models, mkdV, you have all these other models. How do I construct Backlund transformation for all these other models? The idea was to try and describe a phi 1 configuration in my gauge potential and a phi 2 configuration being related by a gauge transformation, by a generator K of phi 1 and phi 2 that transforms one into the other. For the sign Gordon, we know the Backlund transformation, so we constructed the K matrix. And we use the K matrix because, you see, you have zero curvature. And a gauge transformation maps you 0 to 0. So the zero curvature is invariant under gauge transformation by K. Even if it's T3 or T5 or T7, it doesn't matter. So since the X component is common to all the equations, this equation is common to all. But the time component, we assume that the time component also changes by the same K. So, and then we were able to derive the Backlund transformation for T3, which is the mkdV, which is known not too long ago, which was discovered not too long ago. There is a whole book about deriving this equation. For T5, okay, you just plug it there, and then you get for T5, which is not known anywhere. So, and the moral of the story is that the structure of infinite dimensional algebras allowed us to construct all these features in a universal way. This K is a universal object within the hierarchy. One thing that I didn't mention, I used the mkdV hierarchy as an example. I have used that gradation. My gradation was 2 lambda dd lambda plus 1/2 of h. But you can use a different gradation. You can use, for example, a gradation which is lambda dd lambda alone. So this is called homogeneous gradation. Instead of mkdV, you get nonlinear Schrödinger. So nonlinear Schrödinger and mkdV, they belong to different hierarchies, but is a tower of equation of motion, the same way as we have done for mkdV. So the last thing I want to say before I'll jump this. And so what I said is that the construction of the hierarchy involves these 3 ingredients: the algebra, the gradation, and the choice of this E generator. And also, you see, it provides you the construction of all the Soliton solutions, multi-solitons, etc. And one thing that is still not clear and still have to be sorted out is that if you go to Fadiev's book, right at the beginning, he says there are 3 sorts of solutions. Solution with zero vacuum, solutions with constant vacuum that we have seen, and periodic solutions. And periodic solutions have to do with Jacobi theta functions. And Jacobi theta function is some series like this, an infinite series. But it has a parameter, eta, there. When this eta goes to infinity, you take a limit. You can reabsorb terms, and then you end up with something like this, which is precisely the tau functions of the one solid. So the Jacobi theta functions has the one soliton as particular limit. So the question is, how do you systematically construct Jacobi theta function as solutions of those equations in terms of gauge transformation, representations of Cox-Moody algebras and things like that. This is a big question mark, but you see that these things are very similar. So there must be something behind that is still not very clear. So I'll stop here, and I hope this was, the idea was to give you an account of what we can do in classical and continuous integrable models. So thank you very much for the attention.